let's talk about work. An important application of vector line integrals is compute work done by vector fields, which you're thinking about as forces. So in this video, F is our vector field, and we're going to be thinking about this as representing a force. So what are some possible examples of vector fields? We could have that would represent forces. Gravity would be one, or it could be some kind of electromagnetic force. So for example, gravity, and we're just thinking about gravity in let's think about gravity on a particular place on the Earth's surface here on a very small scale. Gravity is a constant force field pointing downwards. It's our approximation here. So the question is, as something is moving through the force field, maybe, our path C is just going to be an object free falling downwards. How much work is the gravitational force field doing? We can compute this with a vector line integral. Of course, this is a kind of approximation to gravity. We should know that on a bigger scale, the further you are away from the center of the Earth, the weaker the gravitational force field is. And of course, really on big scales, when you think about the entire Earth, the gravitational force field is always pointing inwards. And then, of course, the same thing could be said for an electromagnetic force, that let's say that we just have this point charge here, that this is some kind of positively or negatively charged ion, that the force field would be, if these are attracting each other, force field will be pointing straight in towards the point charge. If they're repelling each other, it'd be pointing away. And so then we have this curve C here. This is the path of some particle. How much work is this force field F here doing on the particle whose motion is represented by curve C? And so here's our definition. Let C be a smooth curve parametrized by R of t. It runs between A and B. Let F be a continuous force field over a region containing C. Then the work done in moving an object from the point A to the point B is, guess what? It's just our vector line integral, F dot dr. And so if you're looking for work done by work done by a force field on an object that's moving along, it's just a vector line integral. So calculate the work done by the force field that's given here as a particle moves from 111 to 482 along the curve R of t is given by this right here. All we have to do is, okay, so this is our F. We have our R of t given to us. Life is great. We know we need R prime of t, 2t, 3t squared, and 1. We know we need F of R of t is going to be x squared. X is t squared, so that's t to the 4th. And then negative z is t, so negative t. Negative y over z is going to be negative t cubed over t. So t to the 4th, negative t squared. We need the dot product of F of R of t, dot product R prime of t. So this dot with this right here, this dot with this, and we end up with 2t to the, dot product is not a vector, 2t to the 5th minus 3t cubed minus t squared. And so the work is the integral from 1 to 2 of this expression right here, 2t to the 5th minus 3t cubed minus t squared dt, and you end up obtaining here as your answer negative 89 over 12. So this is actually moving, kind of against the force field. So the work done here is negative.